scientist Tristan from Mexico.
Today we're going to be answering a few essential questions about chemistry, and specific about the atom.
Numero uno, how small is the atom?
Number 2, how fast do electrons travel?
Numero tres, the distance between the nucleus and electrons.
Number 4, how do we explain quantum mechanics and Vector theory?
Numero cinco, the distance between two atoms.
Today we're going to be answering these questions and so much more. We hope you will enjoy this educational film. If the nucleus of a hydrogen atom were 2.5 centimeters in diameter, how far apart could the electron be? Is it A, 0.75 picometers, B, 0.75 centimeters, C, 0.75 meters, or D, 0.75 kilometers? Think about your response now. Stay tuned to hear the correct answer. Over at the Stanford Mall, the team investigates.
Alright, so this is the nucleus of a hydrogen atom, and this is the electron, and so basically...
Figure out how...
Yeah, so you just...
Anywhere?
Anywhere.
Right here?
So, yeah, to the distance you think it would be at.
Say right here.
So right there?
Yeah.
Alright, nucleus of a hydrogen atom, how far away in meters do you think this electron would be in the nucleus?
Meters?
In meters.
2 meters, maybe.
We then went back to Woodside to investigate this question.
Distance between the electron and the nucleus of this atom.
I actually have no idea, but I'm going to take a guess to say it would be about a hair length.
Okay, so that's a good guess.
To scale, how far apart would they be?
Here?
Okay. It turns out that none of these responses provided by the public were remotely correct. The correct answer is D, 0.75 kilometers, or 750 meters. But how far is 750 meters? Well, let's find out. 750 meters is roughly a little more than the distance from J5 to the center of the track. Now imagine the tiny nucleus, 2.5 centimeters in diameter, that little ball on that W. That's how far away it'd be. Scientist Alex Lee and actor Miguel Gutierrez talk about chemistry during their lunch break.
Hey Miguel, there's some nice beans you got.
Hey Alex, that's too much water.
Yeah, did you know that all the water molecules inside this 8-ounce glass of water, if each of them were represented by a bean, you could fill the Atlantic Ocean almost 7 times.
No way, Alex, that's crazy.
Yep.
But how did we calculate this figure? Well, let's do some quick math. A cup of water has about 250 milliliters and weighs about 250 grams. The molar mass of water is 18 grams, which means a 250 gram cup of water would have about 14 moles of H2O. 14 moles multiplied by Avogadro's number, 6.02 times 10 to the 23rd, gives us the number of molecules in the cup of water, 8.4 times 10 to the 24th. Then, we multiply the number of molecules by the volume of each bean, which in this case is 0.25 milliliters, and we get 2.1 times 10 to the 24th milliliters. We then convert that quantity into liters, which ends up being 2.1 times 10 to the 21st liters. Finally, we divide the number of calculated liters by the volume of the Atlantic Ocean, which is 3 times 10 to the 20th liters. This ends up to be about 7. Meanwhile, Oates runs around the track. Think of Oates as an electron. The center of the track, the nucleus. How many laps per second do you think Oates would have to run to match the speed of electron travel? Do you think A, 1 lap per second, B, 100 laps per second, C, 500 laps per second, D, 5,500, or E, none of the above? Take the time now to think of your response. We went to Woodside and asked a few teachers what they thought. One teacher, Mr. Monzo, a world studies teacher, was very close.
I watched a lot of Jimmy Neutron growing up. Say it's about 5,100.
That's right. If you answered D, 5,500, you are correct. The speed of electron travel is a little less than 1% the speed of light, or 2,200 kilometers per second. Convert that to meters, and you get 2.2 times 10 to the 6 meters per second. Each lap is 400 meters. So if you divide the two, you get 5,500 laps per second. If Oates ran at this speed, he could run around the surface of the Earth in just 18 seconds. This model, where Oates is the electron and the W in the center of the track represents the nucleus, can also help explain quantum theory. We know Oates will be running somewhere inside the lanes. In which lane, we don't know exactly, but we can assign a probability to each lane. Let's say Oates' favorite number is 2, so it's most likely he's going to be running in lane 2, but we don't know for sure. We will never know where Oates is until we stop him. Here we can observe Oates running. He stays mainly in lane 1, as that is his preferred lane, and he has the highest probability in lane 1. But what if we want to measure Oates' position? Well, if Oates were truly the size of an electron, he'd be way too small to see. Instead, we would have to stop him with a sensor and measure his location. Here is our sensor. Oates collides, and we detect his location. In the process, however, we disrupt Oates' orbit, and thus modify his position. For this reason, we can't actually detect where electrons are without stopping them and changing their position. This is a fundamental principle of quantum mechanics. This principle is known as the Heisenberg uncertainty principle.
From China
To Mexico.
we hope you learned a lot today. And we'll see you again on another episode of J5 Chem.